In the previous lecture, we introduced the concept of H-bridge inverter, and we had a look at the topology and its working principle. Now we will focus on pulse width modulation, or PWM technique. More specifically, in this video, we will give a definition of pulse width modulation, and we will see different techniques used in single and tri-phase inverter applications. Also, we will go through a comparison between PWM and the square wave, which are among the most used operational modes for solar inverters. Pulse width modulation is a control technique that acts over the switches of the inverter. It has the aim of controlling both the frequency and the amplitude of the output signal. This control is performed by modulating on and off times of the switches, therefore the pulse's width. Apart from power electronics, PWM is also widely used in the digital electronics and signal processing. This technique basically enables the inverter to output a periodic signal towards the AC side of the PV system once opportunely filtered out. PWM method is obtained by comparing two signals. The first signal, called the reference signal, is a high-frequency periodic signal. This signal is either a triangular or a sawtooth signal. The second signal is called the control signal, and it is a pure sinusoidal wave that allows to control the frequency and amplitude of the H-bridge output. Usually, this sinusoid is directly retrieved from the main grid signal. As mentioned before, these two signals are compared in a time frame to obtain a PWM signal that is used to control the switches. At a given instant, if the control signal is greater than the sawtooth signal, the PWM signal is equal to 1, and switches S1 and S4 are closed. If the control signal is lower than the sawtooth, then the PWM signal is equal to 0, and switches S2 and S3 are closed. The two PWM states, alternating over a time frame, determine the output signal of the inverter. The resulting output signal of the switch bridge is a bipolar periodic wave that goes from a positive value of the input voltage Vin to the negative value minus Vin. As we saw in the previous video, such a time-dependent periodic output signal of the bridge can always be decomposed as a sum of sine and cosine waves. Using Fourier analysis, it can be shown that the frequency of the first harmonic equals that of the control signal. Again, all the harmonics of a higher order are disturbances that need to be filtered out before going to the inverter output. To describe the different operative modes of the PWM inverter, it is useful to define the amplitude modulation ratio. This is the ratio between the control signal and the reference signal peak amplitudes. When talking about inverters, the signal considered is the voltage. It is possible to enumerate three modes of operation depending on how the ratio between input and output voltage changes with the amplitude modulation ratio. The first mode is called the linear. Here, if the input voltage is constant, the amplitude of the first harmonic of the output voltage can be modified linearly by changing the amplitude of the sinusoidal control signal. In this mode of operation, the frequency and the amplitude of the output signal can be fully controlled. This mode of operation extends up to the point where the amplitude of the sine control signal is equal to the sawtooth reference signal. At this point, the inverter enters in the so-called over-modulation region, where the output voltage amplitude continues to increase until a specific value of MA, for which the inverter starts working in a square wave mode. In this mode of operation, the output signal becomes a square wave, and its first harmonic amplitude is 4 over pi times the input voltage amplitude. Another possible PWM scheme is called the Unipolar PWM voltage switching. In this case, the switches in the two legs of the H-bridge inverter are not switched simultaneously, as it was in the case of the bipolar scheme. Two signals are needed to control separately the two legs of the inverter in this case. The first leg, usually called the leg A, is controlled by comparing the sawtooth signal with a plus V control signal. On the other hand, the second leg, called B, is controlled with a minus V control signal. In leg A, when V control is higher than V sawtooth, the voltage equals the input voltage, while in the other case the voltage is 0. For switches in leg B, when minus V control is higher than V sawtooth, the voltage equals the input voltage, while in the other case the voltage is again 0. Let's see now what the results of the PWM unipolar scheme are. Once compared the signals as I said before, we obtain the voltage on leg A compared to a neutral point. The amplitude of the pulses is either the input voltage or 0. The same result is obtained for leg B. As expected, since the negative sinusoidal signal equals the positive signal moved by alpha period along the time axis, the two pulse trains are the same, but just translating by alpha period. The output voltage is the difference between the two voltages on the legs. In this type of PWM scheme, the variation in the output is between plus V input and 0, and between 0 and minus V input. Just like the bipolar case, a pure sine can be drawn from Fourier analysis of the output signal. This sine is the fundamental harmonic which carries the real power delivered by the inverter. The most important advantage of the unipolar PWM scheme over the bipolar one is a lower harmonic content, which translates into less signal distortion that needs to be filtered out by the inverter. In applications such as uninterruptible AC power supplies and AC motor drives, three-phase inverters are commonly used to supply three-phase loads. It is possible to supply a three-phase load by means of three separate single-phase inverters, where each inverter produces an output displaced by 120 degrees. Similar to the single-phase inverters, the objective in pulse-width modulated three-phase inverters is to shape and control the three-phase output voltages in magnitude and frequency with an essentially constant input voltage. To obtain balanced three-phase output voltages in a three-phase PWM inverter, the same triangular voltage waveform is compared with the three sinusoidal control voltages that are 120 degrees out of phase. A first phase controls the first leg A. Similarly, the second phase acts on the switches on leg B, and the third phase on the switches on leg C. Comparing each phase with a neutral point, a pulse train output similar to the bipolar single-phase PWM is found. Let's take, for example, the voltage A with respect to a neutral point N. As expected, the signal varies between the input voltage value and 0. Comparing now the second phase B to the reference signal, another output is found. Since the two sine waves have a 120 degrees difference, this time the two pulse trains are outphased by a third of a period. The output voltage between the legs A and B is the difference between VAN and the VBN. What we obtain is the fundamental line-to-line voltage in one phase. In a similar manner, the line-to-line voltages between the legs A and C and legs B and C can be found. Let's now see the main differences between the PWM linear mode and the square wave mode. In the linear mode, the PWM allows us to have both frequency control and magnitude control. The former is obtained by changing the frequency of the control signal. The latter can be performed by changing the amplitude modulation ratio, which is the ratio between the amplitude of the control sine signal and the height of the sawtooth signal. The square wave mode, on the other hand, gives a higher output magnitude since the control signal amplitude is much larger than the reference signal amplitude. This makes the peak amplitude of the first harmonic of the output voltage around 4/pi times the input voltage. Also, the switches are turned on and off only once per period, reducing the switching losses. One negative aspect of this mode is that the output wave amplitude is not controllable anymore. To recap what we have seen in this video, the most used technique to modulate an output AC wave from a rather constant DC input is the pulse width modulation, or PWM. The bipolar type acts simultaneously on the four switches of the inverter and gives a signal that goes from plus V input to minus V input. The unipolar type uses two input signals and draws in the first alpha period a signal that goes from V input to 0, and in the second half period a signal that goes from 0 to minus V input. The pulse width modulation can be applied also to triphase inverters to obtain 3 waves with a 120 degrees phase difference. Finally, we saw a comparison between the single-phase PWM in a linear mode and in a square wave mode. In the next video, we will see the overall configurations of a real inverter.